a robot trying to pick up a banana. Simple, right? Not quite. In the chaotic real world, with clutter, weird angles, and wobbly objects, grasping is a high-stakes guessing game. This paper introduces GraspGen, a clever new way to teach robots how to grasp stuff, using a diffusion model to generate possible grasps, and then a special scoring system to pick the good ones. But here's the twist. The scoring model learns from the grasps the generator itself produces, not just pre-labeled data. It's like a robot chef tasting its own cooking to get better. This trick, called on-generator training, helps the system catch its own bad guesses and improves grasping performance across different grippers and environments. Grab a seat, pun intended, and let's unpack how this grasping framework works and why it's a big deal for robot hands everywhere.
Let's dive into the fascinating world of robotic grasping, which is a fundamental skill for robots. Despite significant advancements, current learning-based methods for 6 degrees of freedom, or 6 DOF, grasping, are not yet user-friendly and struggle to adapt in different settings. The paper builds on recent successes by modeling grasp generation as a diffusion process. They introduce GraspGen, a framework using a diffusion transformer to enhance grasp creation, paired with an evaluator to filter and score the grasps. What's unique is their new training method for the evaluator. To scale this up, they released a massive dataset with over 53 million grasps. GraspGen is shown to outperform older methods in simulations and achieves impressive results on benchmarks and real robots, even with noisy observations. The introduction highlights advances in robot grasping, like data generation and generalization across different environments and conditions. However, critical gaps remain, especially in general-purpose systems. For example, in the FetchBench benchmark, state-of-the-art systems often achieve less than 20% accuracy. The OK Robot project, aiming to manipulate in the wild, reported an error rate of 8% due to grasp failures. These systems tend to perform around 60% accuracy overall, stressing the need for further improvements. Grasping systems aren't yet turnkey, and making them more flexible is a challenge. Traditional methods often require precise information and aren't practical for cluttered settings, highlighting the need for better solutions. Continuing with the challenges faced by current grasping methods, many existing systems, especially those based on contact points, struggle in diverse and cluttered environments. They often require extensive data collection or simulation, which isn't practical for real-world applications. However, recent advances in instance segmentation are simplifying the grasping process by focusing on object-centric models. Enter GraspGen, a new framework that enhances previous methods using a diffusion-based generator and an efficient evaluator. This approach is versatile, handling various gripper types and data completeness levels in both simple and complex environments. One standout feature of GraspGen is its innovative training method using the on-generator dataset. This technique improves performance by making the evaluator more aware of potential errors, scoring faulty predictions lower. The related work section places GraspGen in the broader landscape of 6DOF grasping, which is usually framed as a pose detection problem. It highlights recent developments in grasp sampling and analysis, including models like autoencoders and diffusion models. By focusing on object-centric point clouds, advancements in segmentation models streamline the process, making the system more efficient and less reliant on cumbersome data collection. Now let's delve into the fascinating world of diffusion models in robot manipulation. These models are powerful tools for generating solutions to complex problems in high-dimensional spaces, applicable in areas like policy learning, motion planning, and scene generation. The closest related work involves a diffusion process for known objects without point cloud input. In this context, GraspGen emerges as a solution for generating diverse sets of successful grasps. The goal here is to create varied grasps that handle cluttered environments effectively. It involves generating a top set of possible grasps for an object, ranked and scored, to find the best performers. This ensures that grasps are practically executable, not just theoretically successful. Grasp generation with diffusion frames 6DOF grasp generation as a diffusion model problem, where noise is added to training data and reversed during inference. The model used here is a noise reduction diffusion probabilistic model, which is both efficient and simple to implement. Given the complexity of the grasp space, the model operates in a specialized geometric space. Techniques like translation normalization and object tokenization ensure neural networks function effectively. The method encodes point clouds, enhancing their ability to manage unstructured data efficiently. Let's explore the diffusion noise prediction network's architecture, which you can see in Figure 2. This setup transforms object point clouds into a structured format through serialization, bypassing older methods that required complex hierarchical feature searches. The network processes point clouds and grasps to predict noise, refining the grasping process. During inference, a noise vector is sampled, and the diffusion process is applied iteratively to generate grasps. Hyperparameter search suggests that a small number of denoising steps, like 10, is adequate because grasp dimensionality is simpler than image processing. The training involves a denoising loss, measuring the difference between predicted and actual noise. Interestingly, the network separates denoising processes for translation and rotation, leading to better outcomes. Moving on to grasp evaluation with on-generator training, traditional models often face false positives due to model fitting errors. This training helps mitigate such errors by using an evaluator to filter grasps. The paper shows that grasp distributions from generative models differ from training datasets, highlighting the importance of this tailored training approach to remove failure modes and improve performance. Let's dive into the GraspGen training process, detailed in Algorithm 1. It begins with computing translation normalization, crucial for aligning grasp data. The training uses a diffusion model to simulate grasps, producing an on-generator dataset that mirrors the size of the original offline dataset, ensuring consistency. A key aspect is efficient evaluation. Traditional architectures trained the object encoder separately, but GraspGen simplifies this by reusing the encoder for grasp discrimination, saving resources, and improving performance. The architecture uses a multi-layer perceptron to predict grasp success scores based on object embeddings. The dataset section elaborates on the extensive 6D gripper transformations and success labels used. It follows a pipeline similar to acronym but utilizes a broader range of 3D object data. The datasets are built for specific grippers, like the Franca Panda, ensuring robustness. We then move to experimental evaluation, comparing GraspGen with recent methods like Contact GraspNet and Dex Diffuser. The paper highlights improvements and modifications in GraspGen, like using a point cloud to handle unknown objects and a different model for training. This sets the stage for understanding GraspGen's performance against established baselines. Now let's see the impressive performance of GraspGen in large-scale evaluations. Check out Figure 4, which visually compares GraspGen on the FetchBench benchmark, showing its consistent success over other methods. By reusing existing architectures and skipping less effective baselines, like the variational autoencoder, GraspGen focuses on more relevant comparisons. The full point cloud evaluation of single objects is particularly interesting. Using a complete point cloud without occlusions, the evaluation is conducted on a large dataset, resulting in 1.6 million grasp executions. Precision and coverage are key metrics here. Precision measures the success rate of grasps, while coverage assesses the diversity of grasp positions. Look at Figure 3, which highlights GraspGen's performance on the Franca acronym dataset, where it significantly outperforms other methods. This success is attributed to the effective use of evaluators in training, which help refine grasp predictions. The evaluator focuses on both positive and negative grasps, enhancing GraspGen's ability to distinguish between good and bad contact points. Lastly, the task-level evaluation in cluttered environments underscores GraspGen's robustness, tested using FetchBench. This demonstrates its capability to handle complex, real-world scenarios efficiently. Let's talk about the complexities of grasping simulation and evaluation using FetchBench. The experiments were conducted with the Franca Panda robot across multiple scenes, focusing on detecting and evaluating grasp poses. An Oracle planner was used to establish baseline performance metrics, highlighting issues like collision-free retraction paths and stable but inaccessible poses. Despite these challenges, GraspGen shows superior performance over other methods, with significant improvements in success rates. The sensitivity to occlusions is another crucial aspect. Previous approaches dealt with single-view or complete point clouds, but GraspGen excels by training on a balanced mix, enhancing flexibility for practical applications. Figure 5 illustrates how training on varying point cloud types affects performance. In the analysis of on-generator training, the page addresses the distribution shift between offline and generated datasets. Using Earthmover's distance, it's evident that the spatial distribution of negative grasps is more pronounced. Figure 6 shows the differences in performance, with models trained on on-generator data achieving the best results. This shift justifies the need for a tailored training approach to improve grasp filtering and accuracy. Here, we kick off with ablation studies to refine GraspGen's performance. The analysis reveals that GraspGen's evaluator is more accurate and efficient than previous models, using far less memory. The focus then shifts to translation normalization, where an optimal balance is found between translation errors and recall. Figure 7 illustrates this relationship on the Franca acronym dataset, highlighting the importance of choosing the right normalization multiplier. Examining rotation representation, various methods like Euler angles and Lie algebra were tested, all showing comparable results. A significant finding is the performance boost provided by a new point cloud encoder, which reduces errors and improves recall compared to older models. GraspGen's performance across multiple grippers is impressive, especially with the robotic TUFA 40 and suction grippers. It consistently outperforms other methods, particularly in challenging scenarios like real robot experiments. Finally, the real robot evaluations demonstrate GraspGen's ability to generalize from simulation to reality. Using advanced setups for motion planning and depth estimation, GraspGen proves its versatility and robustness, even in complex real-world tasks. This adaptability underscores its potential for broad applications in robotics. Let's explore the evaluation of GraspGen in cluttered environments, using both simulations and real-world scenarios. Look at Figure 8, which showcases these environments, illustrating how GraspGen navigates complex settings. Adjustments were made for other methods, like rotating the point cloud for M2T2 to align with training distributions. These modifications were crucial for obtaining consistent grasp predictions. Table 1 quantifies GraspGen's performance, presenting success rates across isolated objects and cluttered environments. Achieving an overall success rate of over 81%, GraspGen outperforms M2T2 and AnyGrasp significantly. While GraspGen excelled across most settings, it faced challenges in the shelf and basket scenarios due to kinematic restrictions and collision issues. The conclusion offers insights into GraspGen's broader impact. As a robust framework validated across multiple grippers and environments, it sets a new standard in grasp generation. However, the paper notes limitations, such as the need for better depth sensing and segmentation to improve grasp predictions for certain objects. Future versions aim to address these challenges, highlighting the computational demands of training such advanced systems. Thanks for joining us today. Happy exploring together.